Hi, good morning. Okay, this morning we have a bit of a different session because we are focusing more with our limitation that we have to try to measure quantum observables. And we start with a talk from Baptiste on Top-Antitop reconstruction.
All right, thank you, Federica. So I have about 20 minutes to tell you everything you need to know about top reconstruction. So definitely I'm not going to discuss all of the topics that are there. I'm going to be very Atlas-centric and tell you about things that we are doing now and things that we might do in the future and how they might look for quantum information. And also I'm going to talk a lot about machine learning. And I'm going to try and mix and match the topics. It's a bit of a stream of consciousness, unfortunately. So let's start with the basics of top reconstruction. So as you've heard several times, so we don't actually see these tops in our detectors. We only see the decay products, specifically the electrons, muons, possibly taus, and jets that you get from the W decay, as well as the B jets you get as a telltale sign that you had top production. Specifically on the topic of the B jets, I just wanted to point out the remarkable advances that we've made over the past few years with ever increasing complexity in our machine learning models to identify B jets. And you can see here this almost exponential increase over the past 6 years in our performance to detect these B jets very accurately. So then, based on the fact that we have all these decay products of the tops, we can arrange our TT-bar production into 3 categories. So all hadronic production, where you only have these pairs of jets coming from the Ws, then leptons plus jets, where you have 1 lepton and 1 hadronic W, and the dileptonic final state. So the dileptonic final state is the one that we use for the quantum entanglement measurement in Atlas. And specifically, we're looking at the EMU channel because that removes completely your standard model backgrounds. But you can see it's only 2% of the total data set that we have. So with the LHE, that 2% is still somewhere like 1 million events. But you can imagine like the breadth of physics that we could do if we're able to reconstruct accurately all the other final states. All right, the second part is why do we need to do top reconstruction? So this plot, I think, has been discussed on only one occasion, but this is telling us that we can do spin correlations, so classical angular distributions, with the spinalizing powers of the leptons. And these leptons we reconstruct very accurately in our detectors, so both in Atlas and CMS. It's a very promising first place to start to look at angular distributions in tops, but it doesn't tell you anything about the kinematics of the tops themselves, just about the angular correlations that are preserved by the weak interaction. If you want to do more complicated things like quantum entanglement, Bell's inequalities violations, where you have to access the mass of your TT-bar system as a way of focusing on specific spin structures, you need to perform the full TT-bar reconstruction, so reconstructing both tops and dealing not only with the nice, well-behaved leptons, but also with the neutrinos and the jets. So that's the reason why we need to do top reconstruction. Okay, so looking at the Atlas entanglement paper, so you'll find this little paragraph that I screenshotted from there. And they tell you that the main method used in this work is the ellipse method. So I'll try to explain what that is, but it's only efficient 85% of the time. So in some cases, you try to reconstruct your tops, and for whatever reason, you don't actually get a solution. In those cases, you don't want to lose the 15% of events, and therefore you switch to another method, right? And you try to gain back your efficiency in that way. So what is the ellipse method? It dates back to this paper like 10 years ago. It's been used in a number of Atlas and CMS publications. It's a geometric approach to solving the kinematic constraints that you have on your TT-bar system. So in a dileptonic TT-bar final state, you have these 2 neutrinos, but in your detector, you've only made 1 measurement of the missing energy. So therefore, you have 6 components that you're looking for, but you only have the transverse component of your missing energy. So you have a magnitude and an angle. So the system is under constraint. So therefore, you need to. Sorry? Well, because you can't. You have 2 neutrinos that you're trying to reconstruct, but you don't see the neutrinos separately, right? You only see the sum of these neutrinos in the missing energy, and the missing energy is also contaminated by misreconstruction of the other objects. Yeah. So I mean, you need to come up with this constraint in some way, and that's what I mean here. So you have to make assumptions to try and solve your problem. And the assumptions here is that everything is on shell, which is a reasonable constraint to put on the top physics. So you say that the top is on shell, the W's are on shell, everything has the standard masses from the best measured values and so on. And the second assumption you have to make is that the neutrinos are the source of the missing energy. As I just said, it's not necessarily the case because you have jets, and jets are perhaps misreconstructed. So we do our best to correct for these energy distributions, but it's never perfect. Okay, so then you put yourself in momentum space and you ask, where can my neutrino 4 momenta, or 3 momenta in this case, live? And you find that if you look at the kinematics of your measured B jets and leptons, you have these ellipsoidal surfaces, and intersections of both of these constraints, so the visible decay products of your event, gives you an ellipse, and this is where your neutrino lives. So then this is for one top, you can repeat this for another top, and you get 2 sets of ellipses, the intersections of which would give you a set of solutions. So in this case, you can see that there are in fact 2 sets of solutions. There's one intersection here, one intersection there. What the method doesn't tell you is how to pick which set of solution is the correct one. So in this case, this is the correct solution, and this would just give you a misreconstructed TT bar system. So then you have to come up with additional assumptions, and perhaps you have to rely on your Monte Carlo more than you would like in order to pick what solution is the more appropriate one. In the Atlas entanglement analysis, we don't bias via the Monte Carlo in this way. We just pick the solution that gives you the lowest MTT bar value. So you're trying to put all of your events as much as possible in the entanglement region. Okay, this method is not efficient all the time, so you have to rely on the events where you can't find a solution on the neutrino weighting method, which dates back to the D0 experiment. And by the way, I just wanted to highlight the progress we've made in top physics since D0. So they had in this same paper where they explain this method, they had this value for the top mass, and this one is the latest LHC run 1 combination. So this is our most precise LHC run 1 measurement to date, and you can see what 28 years of top physics does to your uncertainties. And also, like, this central value was extremely close to what we have now. So in this neutrino weighting method, we don't want to make the assumption that the missing energy comes from the neutrinos because we have these mismeasured jets. And instead, what we'll do is scan the neutrino etas. So we have eta of the first neutrino, eta of the second neutrino. That's a 2D plane. And we look at every single value with some resolution in that plane. And we solve our equations for the transverse components of the neutrinos. Only then do we take these components and compare them to the missing energy. We compare them in this way, and we get what we call the neutrino weight. So this weight is maximized in events where the neutrinos represent entirely the missing energy, and therefore where we have very well measured jet in this sense. So it's the possible way of determining that the top reconstruction was done correctly. But still, with this method, you have to scan your etas. So this is very expensive. You have to run these, you have to solve these equations for every single point in your eta 1, eta 2 phase space. And you also have to do it multiple times because you want to check how it depends on the assignments of the B jets, possibly on the dependence of M top and so on. So this is extremely CPU expensive, and that's why we prefer the ellipse method, which is more analytical and faster to solve. I wanted to flash back a slide from Theo's talk a couple of days ago, because this neutrino weighter method, where you try to scan a plane of 2 quantities that are not measured in your event, can actually be applied also to Higgs physics, where this time you're not sampling 2 neutrinos, you're sampling 1 neutrino and the mass of the off-shell double boson. This is exactly what you do, right? You go along this plane and you look for each point on this 2D plane, you compute your neutrino weight, and you see that the weight is maximized in the case where you actually have the correct solution from your truth Monte Carlo. Okay, now I'll switch to the machine learning approaches to top reconstruction. So can we just throw machine learning at this problem instead of going through all of this complexity? Because reconstructing the 2 neutrinos for vectors in the Lepton bar is really the hard part. But maybe you don't need to reconstruct the full system, right? Maybe you can get away with reconstructing other quantities. Maybe you could just regress the mass of the TT bar system. Why would you want to do that? Because you're looking for resonances in TT bar, because you're trying to make a measurement of the top Yukawa, which can be inferred from the mass of the TT bar, or maybe just because you're trying to make your quantum entanglement region more enriched in actually spin 0 singlet TT bar events. Okay, so I want to explain exactly what's going on in this plot. Just look at the 3 curves, and they are there are two conclusions we draw from these initial studies of trying to regress the TT bar mass with Monte Carlos, with machine learning. The first is that if you make your machine learning model more complicated by adding more information about the event, of course you get better resolution. But this resolution is not the only thing you care about. You also care about being unbiased in your estimation of the TT bar mass. And for that, you have to invoke slightly more sophisticated machine learning methods. And in this case, we use just a probabilistic model where the network is predicting a central value plus an estimate of the uncertainty. And once you have this, you actually manage to remove the bias. You still have a slightly large resolution, but maybe that's a promising first step. So that's the general idea. So we want to use as much of the event information as possible, and we want to achieve physically meaningful outputs of our machine learning models. So in the all-hadronic TT bar, this should be quite easy because we don't have neutrinos, we just have visible jets. Everything is measured in the detector, so we can avoid all those problems that I've discussed so far. The problem there is that you have to deal with combinatorics. So you have jets in your events, at least 6 jets, possibly way more. And then you need to pair them up into triplets that you assign to the top or into doublets that you assign to the W. And the very simplest thing that you could do is have just a chi-square that you try to minimize and you run over every single permutation. So this is really highly inefficient, but okay, that's the simplest thing you can do. Techniques in Atlas and CMS have used energy fits of the kinematics where you try to correct a little bit these jets. But okay, it's still the same idea. You have to run over every single permutation of these jets. So again, let's try to throw machine learning at the problem because we want to avoid these combinatorics. And so this is the so-called SPANET model, which stands for Symmetry Preserving Attention Networks. And here, what we input to the model are all the various jets, and we try to embed them into some latent space where the neural network can build whatever representation is more suitable to the task at hand, which is to pair the jets into meaningful objects, or the tops and the Ws. And then these blocks in the middle are what we call transformer encoders, and they come from natural language processing. So think ChatGPT. So this is like the same technology here. It's about looking at the jets all together at the same time as you would words in a sentence and trying to pay attention not only to pairs of jets, but also get some relational information on the whole event. And then where they innovate in this paper is in this last block where you try to build your tops. So here you can have any number of particles, but in our case, we just have 2 tops. And there you can impose what is called tensor attention in paper, but it just means you try to impose symmetries on your topology. So you said the network is going to pick some jets to reconstruct the W, but actually I don't care if this jet is the first W jet or the second, they should be swappable and I get the same object. And the same way, the top should have a B jet and this pair of W jets, but it really doesn't matter if it's the top or the antitop. And so in this way, you build additional symmetries and you get crushing performance compared to your chi-square. So here, just look at the table. The numbers on this side are bigger than numbers on that side. SPANET is very cool. Okay, topographs, yet another way to do physics in all hadronic jets. I will just skip it for now. You can ask me later if you want. What I want to point out here is that these machine learning models give you probabilistic or outputs that look like probabilities, and therefore you could use them to move from reconstruction to classification. So here, we're looking at multiple ways that SPANET can actually tell you about the quality of the event that you had. Did you find the correct solution? So this is the blue curve here, and you can see that we can discriminate events that had the correct top assigned versus ones that didn't. Or even, did you have all the jets that you needed in your events to be able to reconstruct the tops in the first place, or was that, that there was never any solution to be achieved? So I think this is really a powerful outcome of these reconstruction techniques, because now you can use these probabilities to cut on your TT bar events to try and enrich them in some way. Maybe you remove the backgrounds because the backgrounds won't be correctly assigned to TT bar. It doesn't hold for them. But maybe for our quantum entanglement studies, this actually gives you more of a handle on modeling uncertainties, because then you could enrich your region in only well-reconstructed TT bar events. Maybe with a bit of luck, that's where the uncertainties are minimized. Okay, SPANET doesn't just do TT bar. I mean, this is just a little bit of advertising. You can also input any sort of topology. So here we're looking at the separation power between TTH to BB and TTBB. You can also plug in BSM model, so it's absolutely not biased to the sum model in any way. You're not making any assumptions about what the tops actually look like. Okay, so we've discussed orogenic TT bar, which has this problem of picking out the right combinations, and dileptonic TT bar, which has the problem of solving for the neutrinos. Maybe we can find a middle ground in lepton plus jets. So in the lepton plus jets final state, you have a bunch of jets on one side and a lepton and neutrino on the other. But here you can reduce the amount of assumptions that you make, because you can just ask for this W to be on shell, and then you get nice analytical solutions to your problem. Is this useful for quantum information? Yes, we've seen this in multiple talks, because you can actually pick, for instance, the d quark from the WDK, which has a spinalizing power of 1, much like the lepton. This is the motivation for Theo studies in Higgs WW. But also, if you can't pick specifically which one is the Dine-type quark, you can still try to find some optimal way of averaging over these over this hadronic top. And this gives you what's called the optimal hadronic spinalizing power, and this was shown in Dorival's presentation. So again, you can throw machine learning at it, and we can take the same spannet model that's very, very good at dealing with our jets and just extend it with some specified specialized embeddings for the leptons and the missing energy. Looks pretty much the same, and we add to the model the ability to regress some quantities, so the neutrino properties and perhaps MTT bar. You can regress whatever you want on top of that. And here you see the resolution that we get on our neutrino eta. So this is in the analytical solution. You have this sort of funky hourglass shape. This is because you have additional assumptions in your analytical solution. In spannet, you have a much more well-behaved regression of your neutrino eta. So then the question is regressing the neutrino eta enough to help you with your MTT bar? And it looks like it is, right? So here you have this distribution in red. This is the regress MTT bar from this spannet on events with jets and neutrinos. Seems to perform better than all the other models that we've tried, including the analytical solution. You can also see it here. This is your resolution as a function of MTT bar. These are the events that we're interested in for quantum entanglement, for instance. This distribution in red is the one you get from spannet with regression. All the others live here. So you get a nice improvement here. So again, maybe you can use that not to reconstruct the full TT bar system, but just to select events in a more suitable way. Okay, if you want to really solve the neutrino kinematics, you have to use much more sophisticated ways of predicting the neutrino kinematics, and these are conditional invertible neural networks, where you train a neural network on kinematics of your events, and then you ask it to map a normal distribution to the neutrino kinematics. And in this way, you can get access to some form of PDF of the neutrinos, and this has some very cool consequences. So here, let's look, for instance, at the predictions for neutrino eta from various models. You have the true value here. So this is the neutrino eta in your truth Monte Carlo. So this is what you should find. And then you have, in green, two possible solutions to your analytical equation. One of them is quite close to the truth. The other is completely wrong. In principle, you have no way of distinguishing which is which. And when you run the analytical calculation, you have to make some assumption. You have to decide, always I'm going to pick the one with lowest eta, or always I'm going to pick the one that minimizes some other thing. With this neutrino flow method, where you've tried to build some form of PDF of your neutrino over the event, you now have this orange curve. You see that this orange curve realizes that there's a possible solution here, but the solution is very much worse than this one. So if you were to look at this orange curve, so this neutrino flow method, and always pick the one that gives you the, always pick the mode of this distribution, you get something that is much closer to the truth. And indeed, this is what you see in these distributions. Again, the same sort of plot. This is the analytical solution for your neutrino. You have, again, this funky hourglass shape. The neutrino flows is well behaved. When you look at the mass of the leptonic top, so the B-jet lepton neutrino system, this distribution in red is taking the mode of this neutrino PDF, and you can see that it's the one that's much closer to the truth. So potentially a promising technique, and one that we can also apply to cases where we have multiple neutrinos, because it's a neural network. You're just increasing the size of the output. Maybe the reconstruction will get a little bit worse, but in principle, if you have infinite training data, it's not an unsolvable problem. And here we're looking at various kinematics of the TT bar system. In particular, the mass of the top is an interesting one for our studies. You see in orange, this distribution is the mismodeling you get from the ellipse method. In red, slightly better, but much more CPU expensive, the neutrino weighting method. In blue, almost perfectly flat everywhere except in this one bin here, the neutrino flow method where you have two neutrinos. again, this is the same view, but just looking at resolution as a function of MTT bar. Neutrino flows here as the green curve, outperforming the other two techniques. Okay, just as promised, the slide that I took from AJ's talk from the workshop in Oxford that we had earlier this year, because he showed this method that they're working on in CMS that also is machine learning based, but undisclosed machine learning techniques that perform better than your analytical method. And in particular, I'm surprised, extremely well behaved in this threshold region. So maybe, you know, one of the CMS colleagues wants to volunteer some information on what this model is actually doing and if it's related to anything I've shown so far. All right, so that's the end of this little journey into top reconstruction. One thing I didn't talk about is machine learning for boosted tops, which is a whole field of its own. The main takeaways for me here is that reconstruction for classification, I think, will be a very powerful tool, so trying to optimize your selections, rejecting the backgrounds and so on. And in some cases, you don't have to perform the full reconstruction. Maybe you can just get better at doing MTT bar. And also, these methods are not so used so far, so we're still doing a lot of classical analytical solutions to our reconstruction problems. One question that is very important to keep in mind here is how do we propagate systematic uncertainties, and can we actually control them with machine learning? All right.
Thank you a lot, Baptiste.
Thanks a lot. This was very, very useful. I was wondering, when you train these neural networks on this method, I mean, do you have spin correlations on or not? Or...
Yeah. So we train on the state-of-the-art Monte Carlo that we have available in the experiments. Typically, in the studies I've shown, it's PowerEgg, PTA8, HVQ. Okay. We discussed BB4L in Jay's presentation for the same reasons in BB4L, because you don't have information about the truth resonances in the Monte Carlo. You don't have the information about the top. It's harder to train this model. Maybe we can think about techniques to bypass that.
Yeah, because I would always do with and without.
You can in principle. So you could also say if you train only on events that are showered with PTA, maybe you get a bias, and maybe when you train with Herwig, this is how the systematics come back to to bite you in a way. So maybe one way to approach this is to say let's train on spin and not spin. Let's train on Herwig and PTA on MatGraph and whatever.
Yeah, because otherwise, I mean, I would always be scared that if you want to measure spin correlations, when you train your stuff on a sample with spin correlation, you might have a bias.
Right,
finding them or mismeasuring them. I mean, it should be really a kinematical. So this method should be really only kinematical, right? It should not know. I mean, it should not learn the correlations, because if they learn the correlation from the Monte Carlo, then you have a bias possible.
Right, but it's also a bias that you would see once you start looking at your observables of interest, whether spin correlations, entanglement, whatever. You would run the same reconstruction that you got from these machine learning models on your standard model assumption and on stress distribution. And this is exactly what is done in the quantum entanglement measurement. We check, of course, for various values of these. Are we biased in any way? And in that particular paper, we find we're not biased. Here, with the machine learning method, you would have to actually check it. But...
Yeah, so related to this, you mentioned twice that you choose the solution which makes your invariant mass smaller. Isn't that also a bias?
It's an assumption. So if you have these ellipse methods or the analytical solution in the lepton plus jets, you have potentially two solutions. For the ellipses, you can get up to 4, and there's only one that's correct, right? So when you look at data, you have these 4 solutions. It's only in the case of the Monte Carlo that you can pick which one is the best. So you have to come up with some sort of heuristics to decide. When I look at data, I will always take this approach because I found that in Monte Carlo, maybe it maximizes my chances of picking the one. Picking the lowest MTT bar is one arbitrary way of going about it, because it forces your events to end up in your region, and therefore you don't have statistical power.
But I don't understand what you mean by that. I mean, why you want to force events to go into the lowest mean? You don't want to force anybody to go anywhere.
Yeah, but it's one choice that makes sure that your events that had a low MTT bar mass in the truth stay in that region. And okay, you invite some contamination from the higher regions, but you make sure that your entangled events are still there. So in a way, you could pick some other heuristic and you would push your entangled events out of the signal region, which is maybe more undesirable.
Maybe I can jump in with a comment here. So you are right that this is somehow a bias because you're deliberately asking that you always want to have the lowest MTT bar. For the experimental point of view, it's not too much of a problematic bias because you make sure you do the same thing on your Monte Carlo as you do on your data. So you hope it doesn't introduce any different behavior in this way. But if you didn't want to have this bias, what you can also do is if you've got when you have these two solutions, you could just take both. And then you end up with, instead of a bias, you end up with a combinatorics background because you have to take both cases. And when we tested this in the past, it doesn't really make that much of a difference. You might have to be more careful if you were looking for a new physics sample where you were looking for a resonance or something like this. But for spin correlation measurements and charge asymmetry measurements and other properties measurements in the past, when we checked this, it has never really introduced some really dangerous biases. And you can check this by, for example, running the reconstruction again with these settings on a sample with no spin correlation. And so, you can check it on things like this. So at least to the precision of the measurements we've done so far, we've never observed this to be a problematic bias. I mean, it is one, but it's like Baptiste says, you either have to take a choice or you have to take both combinations and end up with a new background.
I mean, a priori, I don't see, I mean, I would prefer to have less events, but they're pure than more events that are dirty, right? I mean, a priori, I don't know. I mean, you might see after, but okay. So no, sorry, last question. So in the first slide, right, you second slide, you show these spin correlations, right? So I mean, that obviously there is something that doesn't fit. I mean, there is a problem, right there. And so are you guys working on this? Or?
Yes. Marcel may want to comment as well. Yes, this is something we will do again in the future. I think it's not true to say that we completely understand where this slope comes from yet. We saw that the next to next leading order corrections bring you a little bit closer, but only in the fiducial particle level region and not in the full phase space, which is still not particularly understood. I think Chacon and Rene and all these guys think that it's something to do with the extrapolation that we're doing, but we don't know yet. There are newer models on the market, so this BB4L code that did look like it was getting better, but now we're not too sure again about this. So I think it's probably fair to say that this is still not resolved. To what degree it is still not resolved is not clear, but I think both Atlas and CMS will have more to say on it in the not too distant future. Maybe Marcel wants to.
Yes, well, you've said most of it. I think for both plots, our hope is that theorists can come up with better predictions. But PowerHack HVQ with the top decay with a bright Wigner and leading order is formally not very accurate for spin correlations or entanglement. BB4L ought to be better, but it's been a bit of a struggle to get a stable version for that. And then, of course, you don't have tops in every event anymore, so you can't easily compare. At fixed order, we have much more precise predictions, and they do go in the right direction. But the Atlas and CMS measurements on this quantity on delta phi inclusively agree, and we think that there's something wrong with the theory, and if it's practically leading order, you don't expect it to do very well to start with. And yeah, the frustration is a bit that there are much better tools already out there, but we can't seem to package them in a way that we can use them.
Thanks.
Sorry, can you go to the last but one slide? Okay, so which kind of topology is this?
So I think this has to be Top-Antitop because it was shown.
Okay,
in the
now because I see here that around the threshold, the analytical method with the ellipse method that works even better with respect to the machine learning based. So how does it compare with Atlas? Because it seems now I want to be sure that what is called the ellipsoidal method is basically the same that you described before. Because I know that CMS actually at the end it performed also some smearing around the assumed value. It is something that we tried in the past, and if I well remember, it worked even better with respect to the standard ellipsoidal method. Okay.
So the exact implementation I can't
Okay.
comment on, but we do have the smearing. So there are multiple ways that you can check the method again, either by smearing the masses of the constraint, so the mass of the top, the mass of the W. Maybe that's one way you get the smearing. Another one is by smearing the jets. At the leptons to some very, very tiny fraction. So in the Atlas Quantum Entanglement paper, this smearing is applied.
Okay.
In the other studies I showed here, I mean, this is Delphi, so I wouldn't take that too seriously, but it does seem that machine learning can get better than ellipse. Here in this case, I would let AJ comment his around.
Thank you.
Are there any other questions? No? So thanks again, Baptiste.